Friends, today I am now going to discuss about the finite well. Finite well or finite box in case of quantum mechanics. So let's discuss. It's very important in case of quantum mechanics and and little bit tougher than infinite square well problems also. So let's discuss. So before discussing about finite well, let's talk about what is actually finite well and why we are calling it finite. So, in case of infinite well, what we have seen? In case of infinite well, we have seen that. Let's draw it correctly. In case of infinite well, we have seen that here at the boundary, suppose it is 0 to L or minus L by 2 to plus L by 2, whatever. In the boundary, potential was infinite. Potential was infinite. Potential infinite means at the infinite potential at the boundary, the wave function vanishes. At the infinite potential at the boundary, wave function psi tends to 0 at the infinite boundary. So that was infinite well. And in case of infinite well, the particle remains in case of bound state. Particles remains in the bound state. So what's difference in case of finite well? So let's discuss the difference between the finite well. Ideally, you can say that there will be very small. Ideally, that infinite square well, if we instead of infinite square well, if we assume the potential at the boundary is not infinite. That means if we assume that the potential at the boundary, here it is minus L by 2 plus L by 2. Okay. Here it is minus L by 2 plus L by 2. Here it is region 1, region 2 and region 3. Okay. And here the potential suppose V0 and here the potential is also suppose V0 and inside the box for the potential of the particle is 0. So we can say in case of finite wells, the potential is what? Potential is finite at the boundary. In case of finite wells, the potential is finite at the boundary. Potential remains finite at the boundary, and one of the most important difference between the finite well and infinite well is the number of bound state. The number of bound state in case of finite well is lesser than infinite well. Means in case of infinite well, the bound state is more than the finite well. Now you can see from the finite well that potential is even. Potential even means what? Hamiltonian also will be even. Hamiltonian even means what? It will commute with parity operator. Parity operator, it will commute with parity operator means the wave function can be even and odd both. Okay. So in case of finite well, we will write the wave function. We are not going to derive it. In case of finite well, first draw the finite well. In case of finite well, there will be two wave function. One is even wave function. Potential is even, but wave function will be even and odd both. Okay. Here it is region 1, region 2 and region 3. Here it is V equals V0. Here it is V equals V0. So in case of finite well, we got what? We got that potential is even potential. Even potential means Hamiltonian is also even. Hamiltonian is also even. Even Hamiltonian means what? Even Hamiltonian means it will commute with parity operator. And now we know that parity operator has parity operator is what? Parity operator will produce two eigenvalues plus 1 and minus 1. So potential of the finite well will be even and odd both. Okay. So for finite well, even potential will be even wave function will be for the finite well will be 1 in the region 1. It was decaying. Yeah. In the region 1 it was decaying, let us call it a u to the power alpha x. In the region 2 it was oscillating wave function d cos beta x, suppose it is d cos beta x. In the region 3 it was again decaying, and let us consider it is f e to the power minus alpha x. So let's discuss about the physical significance of this. So graphically, how we can say bounce state? Bounce state explanation graphically. How we can say that potential in a system, the system is remaining in the bounce state. So see here, in case of finite well, okay, in case of finite well, let me change the pen color. In the boundary region, the wave function is what? The boundary region wave function is decaying. Wave function is decaying. Decay. Outside the boundary, okay. Outside the boundary, wave function is decaying. But in between in the middle of the box or middle of the well, the wave function is what? In the middle of the well, wave function is oscillating. So whenever this condition will be happened, that besides the boundary the wave function is decaying, but inside the well the wave function is oscillating type. So in that case we can see that particle is in the bounce state. In that case we can say the particle is in the bounce state. Yeah. So for even potential, we can say this is a bounce state. Here it is a region 1 decaying state. Region 1 decaying state. So it will be like e to the power alpha x. Here even potential in the region 2 oscillating wave function. So it will be cos beta x. Suppose cos alpha x, cos beta x, whatever. And in the region 3. Here it is decaying, it is also decaying, so e to the power minus alpha x type. So this is the thing that we will get in case of finite well. So in case of finite well, so let us write again about that wave function of the finite well. So wave function in the region 1, let me change the pen color. Okay. So wave function in case of region 1 finite well, the wave function is such that a e to the power plus alpha x. Wave function in the region 2 was such that d cos beta x. Okay. And wave function in the region 3 was, let me take the pen. Wave function in region 3 was f e to the power minus alpha x. Now you can say me that what is alpha and beta here? What is alpha and beta here? So let's discuss what is alpha and beta. It is actually nothing but wave number, and why it is plus alpha x, why it is minus alpha x, I am going to explain that also. So let us discuss that. What is alpha and beta? Alpha and beta. Alpha and beta is actually wave number here, because whenever you are drawing the finite well potential, here you are drawing the finite well potential, here it is V0, here it is V0. Inside potential, inside the box, inside finite well, the potential was 0, V equals 0. So here what will be the wave number? So wave number here it will be root over 2m e minus 0. Actually the format is root over 2m e minus v divided by h cut square. So it will be like that, root over 2m e minus 0 h cut square whenever e greater than v. Okay, e minus 0 h cut square. So that will be what? That will be beta. Yeah. So what is beta here? Beta will be root over 2m e minus 0. Actually the format of wave function is root over 2m e minus v by h cut square. So here it will be 2m e minus 0 by h cut square. So we can write beta as root over 2m e by h cut square. So now what is alpha? Alpha is actually the wave number. So propagation vector alpha is actually also the wave propagation vector here and here along outside the boundary, decaying state actually. Here v0, here v0. So alpha can be written as alpha equals root over 2m e minus v0 divided by h square. Yeah, root over 2m into e minus v0 divided by h square. So let's apply the boundary condition or continuity condition of continuity for case of continuity condition in case of finite well. Continuity condition. So what is continuity condition? So here it is a finite well, minus L by 2 to plus L by 2. Okay. So here at the boundary wave function there will be, it is continuous. Here it is the wave function. So here phi 1 at x equals minus L by 2 equals phi 2 at x equals plus x equals minus L by 2. So we can write phi 1 at x equals minus L by 2 equals phi 2 at x equals minus L by 2. So it is one condition. It is one condition for wave function. So we can write properly the condition of continuity is phi 1 at boundary minus L by 2 equals phi 2 at boundary minus L by 2. Another condition is derivative of phi 1 at minus L by 2 equals derivative of phi 2 at minus L by 2. We have to satisfy this both condition. So what we will get satisfying this both condition? Phi 1 at minus L by 2, what it is indicating? Phi 1 at minus L by 2 actually, phi 1 equals what? Now first let me discuss why phi 1 equals e to the power plus alpha x and phi 3 equals if e to the power minus alpha x. Actually see, if we do the symmetry, actually it is even function, even potential. So here it is decaying. Let me draw that finite well. Here negative x. Here x tends in the left sides of the potential well, x tends to minus infinity. X is going to minus infinity. So phi 1 will be a to the power alpha minus infinity. A to the power minus infinity. That means phi 1 is going to be vanished and it will be 0. The negative side of the well. So we have to take plus alpha x, because here if we write the wave function at the region 1, a to the power minus alpha x, and if x goes to minus infinity, so a to the power infinity, so wave function will blow up. That's not possible, na? So here it will be x phi 1 equals a e to the power alpha x, and here at the positive side a to the power minus alpha x, because if here x goes to minus infinity, here if x goes to plus infinity, then this wave function will be vanished. That wave function is satisfying the condition of wave function. But if we put x tends to minus infinity, it will be blown up. That's why here it is being f e to the power minus alpha x. So whatever, now put the condition of continuity. What was that condition of continuity? Phi 1 at minus L by 2 equals phi 2 at minus L by 2. So what it will a to the power alpha x at x equals minus L by 2, it will give a to the power alpha x, a to the power alpha x at x equals minus L by 2 equals d cos beta x at x equals minus L by 2. Let me write properly. A e to the power alpha x at x equals minus L by 2 equals d cos beta x at x equals minus L by 2. Okay. So if we put minus L by 2 value, a to the power minus alpha L by 2 equals d cos beta L by 2. Not cos of minus equals cos of minus x equals cos of plus x. That is the condition. So give it here the equation number 1. So a to the power minus alpha L by 2 equals d cos beta L by 2 this thing we are getting here. So now if we apply another condition is what? Second condition of the continuity. Let me write properly that condition. Phi 1 prime at x equals phi 2 prime at x equals minus L by 2, means derivative of the wave function should be continuous at the boundary. What I am saying, derivative of the wave function should be continuous at the boundary. So phi 1 prime x at x equals minus L by 2 and phi 2 prime x at x equals minus L by 2. So if we write this, what we will get? So phi 1 prime x, a to the power alpha x. A to the power alpha x means what? Alpha a e to the power alpha x equals d cos beta x. D cos beta x, so beta d minus sine beta x at x equals minus L by 2. At x equals minus L by 2, these will be alpha a e to the power at x equals minus L by 2. Alpha a e to the power minus alpha L by 2 equals minus beta d sine beta L by 2. Let me write properly. Minus beta d sine beta L by 2, sine of minus beta L by 2, that will be minus, so it will be plus. So let us write properly again. So by the derivative of the wave function should be continuous the boundary. By this condition, what we will get? We will get alpha a e to the power alpha L by 2 equals beta d sine beta L by 2. This is one equation. Another equation is a e to the power minus alpha L by 2 equals d cos beta L by 2. So these are two equations. So divide these two equations. Suppose name it as 2 and it was given as 1. Now divide two equations, 2 by 1. 2 divided by 1. What we will get? By doing 2 divided by 1, we will get beta L by 2. Let me write clearly. 2 divided by 1, by doing that, we will get beta L by 2 tan beta L by 2 equals alpha L by 2. Now if we put it as beta L by 2 as P, alpha L by 2 as Q, if we get this P and alpha L by 2 as Q, so we will get what? We will get P tan P equals Q. This is the transcendental equation. This is an transcendental equation in case of finite square well. Transcendental equation means we can solve it only by graphically or numerical method. Graphically or numerical method. Yeah. We can solve it by two ways only. One is graphically, another is numerical method. So for even wave function, we will get P tan P equals Q, where P equals beta L by 2, Q equals alpha L by 2, where beta is what? Beta means root over 2me divided by h cut square. Alpha means root over 2m e minus v0 divided by h cut square. So now we will get another condition, p square plus q square equals r square. What is r here? R is actually radius. Radius of what? We will discuss that also. R is actually root over mv0 L square by 2 h cut square. So now if we try to solve graphically, then what we will get? Let's draw the graph of that wave function. If we draw the graph of that wave function, we will not discuss in detail today that graphical solution. We will discuss graphical solution next day, but for today I am showing you how to draw that 0, pi by 2, pi, 3 pi by 2. I am giving you an example. Here it is even state, odd state, even state, and it is odd state. Suppose this is the circle radius, so this will be r. So we'll discuss in detail in my next session about the solution of this graphical method. I'm just showing you how we will calculate, but this is the main method for the even potential. For even potential and even wave function, we will get three relation: p tan p equals q, another is p square plus q square equals r square, r equals root over mv0 L square by 2 h cut square, and where p equals beta L by 2, q equals alpha L by 2, even wave function. Similarly for odd wave function, we will get p cot p equals q, p cot p equals minus q, this relation 1, p cot p equals minus q, others are same, p square plus q square equals r square, r equals root over mv0 L square by 2 h cut square. Same thing. In the next video, in the next session, we'll discuss, in the next video, we'll discuss solution of this finite square wave by graphical method. That was going to be very, very important video. So hope you will all learn very new things from that video. So thank you so much for patiently watching my video. That's all for today. So thank you.